I want to just, without any further ado, just get on to the talks. I'm Eric Aspog. I'll be giving one of these talks. I was told by Pascal to rule with an iron fist, but we're starting a bit late, so I'll just keep the talks on schedule. So I would just like to introduce our first speaker, who is Pascal Rosenblatt, who will be speaking on the origin of Phobos and Deimos, an overview. He's also my session co-chair. I'll be giving you, it's a 15-minute plus 5-minute Q&A, so I'll be giving you a little 12-minute alert.
Okay, so again, good morning to everybody, and I will start this workshop. This is a very great honor for me by giving you an updated overview concerning the origin of Phobos and Deimos. As you know now, this is a very puzzling question, and there is two unmembered scenarios. Either Phobos and Deimos are asteroids captured by Mars, or they have been formed in situ in Mars orbit by accretion of debris. There is also some kind of hybrid scenario that has been proposed, which are in fact a kind of combination between these two unmembered scenarios. So the capture scenario is based on the observation of Phobos and Deimos, and in particular their low albedo, their small size, their irregular shape, and their highly crateric surfaces, which are very similar to the surface of asteroid. And in addition, in the case of Phobos, the surface crater air retention has been estimated as old as 4 gigayears, and this is as old as for many asteroids. But the main support to the capture scenario, this is really the visible and near-infrared reflectance spectra of the surface of both moons, which are very similar to those of the D-type asteroid. And this is really the main support to this capture scenario. But to work, and so there is many spectra collected since the space area with the Viking mission, the Phobos 2 mission, and also from some rover at the surface of Mars, and also from Earth-based telescope. And the most recent spectra that has been collected has revealed a very tiny absorption band centered around 0.565 micron. And this has been interpreted as the signature of a primitive material which could compose the primitive asteroid. And so in turn it suggests that Phobos and Deimos could also be made of material condensed in the solar nebula but away from the orbit of Mars. And this is really the main strongest argument in favor of the capture scenario. But to work, the capture scenario must explain how to change an orbit just after the capture, which is expected to be in the ecliptic plane and very eccentric, into the present near-circular and near-equatorial orbit with Phobos close to Mars and Deimos a little bit above the synchronous orbit lying at 6 Mars radii. And so already 30 years ago, many studies have been done, and they have all proposed the tidal dissipation in Mars and in the Moon as the mechanism to provide these very huge orbital changes. But numerical computation have shown that it was impossible to get from the orbit of a capture object the present orbit of Deimos over the edge of the solar system. It was likely for Phobos, but if one assumes tidal rate properties inside Phobos much closer to those of ice. And so far, we know that Phobos is not an ice cube. So there is a problem here. I made a recent study to update this calculation, and I found exactly the same results, and especially the difficulty to change the inclination from the ecliptic plane to the equatorial plane. Other people have proposed to assume that capture was done in the Mars equatorial plane, but to work this hypothesis, we need to have the distance to Mars that quickly decrease below about 13 Mars radii in order to further maintain the orbit of the captured object in the equatorial plane. So, in fact, following the variation of orientation of the spin axis of Mars. And so we need another efficient phenomenon to change the orbit in addition to tidal dissipation. And it has been proposed some idea like drag effect in the primitive Martian planetary nebula. But this nebula survival time has to be relatively short to avoid the crash of the captured body onto Mars. So this drag effect has not yet been studied as for the tidal dissipation process. But in front of the difficulty to change the orbit, it has been proposed alternative scenario with formation in situ, so formation already in the equatorial plane of Mars. And for instance, it has been proposed a giant impact scenario, and this is based on the same scenario proposed for the formation of the moon on the Earth. This scenario assumes that a giant impact hits the proto-Mars, formed an accretion disk around Mars with a mass of up to 10 to 19 kilogram. And within this disk, moonlets formed, but most of them formed inside the synchronous orbit. And so the orbit reset back rapidly to Mars. But as it is a very happy scenario, I would say, 2 moonlets survive, corresponding to Phobos and Deimos. So this is a scenario, quite interesting, but we have only a few physical modeling that have studied this scenario. And the first one was published in 2012. And in this model, the author considered a compact disk of debris formed by a giant collision close to the planet. And from this disk, it is possible to form moonlet just at the Roche limit at 3 Mars radii or distance from Mars. And once formed, the orbit of the moonlet are driven by 2 opposite forces, one corresponding to the tidal pull of the planet, which makes the orbit reset back to the planet, and the other one corresponds to gravity interaction between the moonlet and the disk, which tend to migrate the moonlet outward from the planet. And so numerical simulation have been done, and it has been shown that it is possible with a disk with a mass of 10 to 19 kilogram to produce a series of moonlets with the most massive corresponding to the mass of Phobos. And they migrate outward, but they cannot cross the synchronous orbit. So that the orbit reset back to Mars when the disk emptied. And finally, after only 200 million of years, all the system disappeared. And we know that the surface age of Phobos is 4 billion years. So this is not consistent with this observation. And it has been concluded that accretion from a compact disk of debris alone doesn't work to explain the formation of Phobos and Deimos. A most recent work was published by Citron and co-author in 2015, and has made a simulation of the formation of a disk of debris around Mars after a huge impact having formed Borealis Basin in the northern hemisphere of Mars. And what is interesting in this study, it is that it shows indeed that we can form a compact disk close to the planet, but also a less dense disk extended beyond even the orbit of Deimos. So I think that the next talk by Salmon and co-author will show us more about this kind of simulations. But with my co-authors, we have redone the simulation by Citron and co-authors, and I show you here what we have obtained. Here, this is the surface density of the disk formed after the huge impact having formed Borealis Basin. Here, this is the distance to Mars in Mars radii. And indeed, we can form a massive compact disk just below the Roche limits that contain, in fact, more than 99% of the total mass of the disk. And we can have an extended, less dense extended disk up to the orbit of Deimos. But this another point quite interesting in this simulation, this is that, in fact, you can see there is 2 colors here, the white and the purple, and that correspond to material from the impactor and the target. And you can see that in this disk, we can have a mixture of both material. So this is important for the future sample return mission. But this kind of simulation, in fact, they lack resolution, and they can only monitor particles with a mass much larger than the mass of Phobos and Deimos. And so they leave open the questions. Can Phobos and Deimos form in this outer disk? So to study this, okay, and also another point important, the challenge to win by this accretion model, this is to form only two bodies, the more massive just below the synchronous orbit, in order to be able to reach the present Phobos orbit after 4 gigayears of tidal dissipation effect, and the lighter just above the synchronous orbit, very close to the present position of Deimos. So in order to study this problem, in order to try if we can find a solution, we have modeled the evolution of the inner disk as from the simulation of giant impact. We use, as for our study published in 2012, an hydrodynamics model for the evolution of the dense compact disk. And here, this is the result with the disk surface density in the y-axis, and in the x-axis, this is the distance to Mars in Mars radii. And you can see that it is possible to rapidly form a moonlet and a series of moonlets that that migrate outward from the planet. And the most massive inner moon, with a mass of 10 to 19 kilograms, reaches the distance of 4.4 Mars radii, which is still inside the synchronous limits. And we have added, and this is what is new, the evolution of the outer disk. And so as the simulation of disk formation cannot provide us with a realistic distribution of the mass inside this outer disk, we have assumed a satellite embryo distribution on the basis of what is usually done for the mass distribution of embryos in planetary disk. And so we have then made symplectic integration of this satellite embryo motion over 500,000 years. We have taken into account inelastic collision during close encounter between embryos and leading to accretion. And the most important, we have considered the perturbation, the gravitational perturbation of these satellite embryos by the big inner moon produced in the inner disk at the Roche limits. And I show you here one of our nicest results. And this is on the y-axis, we have the semi-major axis of the orbit of the satellite embryo distribution, the initial one we have taken in this case between 4.6 and 7 Mars radii. And in the x-axis, this is time. Okay, and you can follow the migration of the largest inner moon here and the location of the resonances associated with the position of this moon. And as the largest inner moon migrates, the location of resonances migrate with it, and they favor, in fact, close encounter and accretion of the small satellite embryo, forming bigger bodies, which continue to accrete together. They can even leave the resonances, and the system eventually ends up with two small satellites, the more massive below the synchronous orbit and the lighter just above it. And in this example, the masses of these two small satellites well correspond to the masses of Phobos and Deimos. So this result has been very recently published in Nature Geoscience. Of course, as it is simulation of dynamic system, just one point. This is now, I want really to emphasize on the fact that the resonances are the key mechanism to explain this process. And I show you here the evolution of the eccentricity of the orbit of the satellite embryo. And when the resonances crosses this orbit, it excites the eccentricity, facilitating close encounter and finally accretion into two small bodies. And so we have made a lot of run by varying the initial condition, like the distribution of satellite embryo, starting not at 4.6 Mars radii, but at further distance from Mars. And we have obtained in 1/3 of our cases one more massive satellite below and one lighter satellite above the synchronous orbit, as it is represented here. We have even in 10% of the cases, the satellite masses very close, in a few percent, close to Phobos and Deimos masses. So I will be able to show you much more detail around all this, about all these runs at the poster session. Just to finish this model, we have also looked at the tidal evolution of the orbit of the two outer satellites formed by this accretion process. And we have shown that it is possible for this outer satellite to reach the present orbit of Phobos and Deimos after 4 gigayears of tidal evolution, assuming very reasonable value for the tidal rate properties inside this body. And the last point, very important, I think, this is that the giant collision scenario can also be reconciled with reflectance spectra. And indeed, in a very recent publication by Roney and co-authors, it has been shown that condensation from gas to solid is expected to provide sub-micron size grain. And these very fine grain are expected to have spectral properties very close to the spectra of Phobos and Deimos and even of the G-type asteroid. And in turn, it suggests that the spectra of Phobos and Deimos reveals in fact, the condition prevailing at the formation of Phobos and Deimos, so that the material may be condensed at Mars in the outer disk in similar condition as material condensed away in the solar nebula. And finally, we don't need anymore to capture material away from Mars to explain the spectra of Phobos and Deimos. And so here, this is my summaries. And I think that very recently we have made a major breakthrough in our understanding of the formation of Phobos and Deimos. They may have been accreted in the outer part of a debris disk from a giant impact. And this accretion, and this is due to accretion of outer small debris triggered by inner larger moons, now disappeared due to Mars tidal forces. And even the giant impact scenario can be reconciled with spectral data. And so now we are waiting for sample return mission prepared by Japanese and European and Russian Space Agency in order to validate or not this scenario. Thank you very much.
We have 3-4 minutes for questions. Especially if you can get spectral similarity with debris condensed in the region of Mars, why do you need any giant impact? What is the compelling reason to have planetary material mixed in? Because debris coming from the region of Mars, small asteroids on not very eccentric orbits, is going to be capturable from either a close tidal encounter, partially capturing it, or a collision with something very small, disruptive collision, allowing debris out there. And then it's not right near the Roche lobe. It can easily be in the region where Phobos and Deimos are thought to have formed. And therefore, you don't need just the tail end of a big distribution of material that was thrown up. You can get something captured of order the masses of current Phobos plus Deimos, and therefore, with a small amount, should be much more common.
Okay, but as far as I know, there is no modeling of this kind of scenario. This is certainly something to look at. But the main major problem I see, this is how to explain only two bodies. And you really need to have your collision close to the synchronous orbit in order to have a Deimos just above and one Phobos just below. So
if Phobos was the biggest one, well, if there were significantly larger things closer in, they would have been lost to tides. And if Phobos was the largest of the surviving bodies, was larger than some of the things a bit inside of it, it would have caught up with them and accreted them. Tidal evolution.
I just wanted to comment on Jack's comment, but I think the issue is that if you have a tidal disruption, and so essentially all the material effectively is going to be into a disk. You can imagine a debris disk coming from that gets the same factor, but it's all inside the Roche limit, right? In order to get Deimos, you have to have some mass which is going to be outside the synchronous location, because there's no other way to get it there by tides. So I think you would have to have some way for tidal disruption to give you an extended disk to do things. I think that's going to be very hard. So I think that's one of the reasons why it's been hard to do this. I think the giant impact models have hope of putting things beyond synchronous, and that's why you can get Deimos, and I think that's why the giant impact is more viable. Jack's giving me a look. So.
Yeah, no, I think the material will be highly disrupted inside, and it will be, a lot of it's just going to go on escape orbits, and the things that aren't going to go on escape orbits, many of them will be on high eccentricity captured orbits of the collisions.
Right, but collisions are going to bring them all. I would assume collisions are going to bring down because their periops is going to be inside the Roche limit, right? So then essentially all they're going to be circularized inside the Roche limit too, right? Was that a yes or a no?
No.
No? Okay.
No.
I'd have to. It'd be interesting to see that.
All right, Andy? I think the spectral evidence couldn't be used like that, because I think the reason that we wanted to capture it in the first place is because we needed to capture something that was red. And if you're going to capture it from something nearer to Mars, you're not going to have something that has those spectral properties. It's going to look like a typical S-class kind of asteroid. So if you could create red material via recondensing stuff in the impact, which it looked like from back here, it looked like that was what the paper figures were showing, then you would need to either capture it from the outer belt or you'd need to do it this way. You couldn't capture it from nearby material.
There's going to be a discussion session at the end. And there's a quick.
Probably not.
Okay. There'll be
Okay.
Yeah, there's going to be a broader discussion when we wrap up this morning session. The next speaker is a related topic.